Student friends, in yesterday's lecture, we studied the definition of an oscillator, and where we have studied that oscillator is an electronic circuit that converts DC into AC. It is the circuit that produces the output without any input. Then we have studied the types of oscillators. Depends upon different factors. The oscillators may be LC oscillator, it may be RC oscillator, they may be audio frequency oscillator, or they may be radio frequency oscillator. They may be sinusoidal oscillator, or they may be non-sinusoidal oscillator. Then we have studied the positive feedback by considering the theory of feedback, and where we have concluded that positive feedback is essential, and in that part, if positive feedback is there, and suppose 1 minus KAV becomes equal to 0, then KAV becomes equal to 1, then gain of that particular amplifier circuitry becomes infinity. When the gain of amplifier circuitry becomes infinity, then input becomes 0 and output becomes maximum. So that gives the definition of an oscillator. That is, it produces the output without any input. Hence, we have considered the concept of positive feedback. Then we have studied the Barkhausen criteria to sustain the oscillations. To sustain the oscillations in an oscillator, the first condition is that the loop gain, that is KAV, should be greater than or equal to 1. And this is possible provided there is a positive feedback. And this positive feedback is obtained by introducing no phase shift between input and output of an oscillator. That is, when phase shift between input signal and output signal generated is either 0 degree or 360 degree, then oscillations are definitely going to be sustained by considering that there is a positive feedback. So these two conditions, we can call it as a Barkhausen criteria, must be satisfied by means of an oscillator circuit to sustain the oscillations. Student friends, today we are going to consider how oscillations are generated in the LC tank circuit. Basically, tank circuits are of two types, using which how oscillations are going to be generated. LC tank circuit has the meaning that the inductance L and capacitor C are going to be connected with each other. In this particular figure 1, we can say the inductance L and capacitors are connected in parallel to each other, provided the switch is closed. As long as switch S is open, the circuit will not work at all. Such a combinational circuit, we can call it as it is the LC tank circuit. To begin to make you understand that how oscillations are going to be generated, let us suppose a charged capacitor C with the polarity positive charges on the upper side, negative charges on the lower side, which is fully charged, having the electrostatic charges which are stored on that, is connected in parallel to the inductance L. In one sentence we can say, when charged capacitor is connected in parallel to the inductance L, in this particular figure, simply just you close the switch. Means in this position, when you close the switch, naturally current through the capacitor will start flowing and it will start passing towards the L by discharging the capacitor C. In other words, we can say the capacitor will starts discharging. Discharging current will flow according to equation that E is equal to 1 minus e raised to minus t upon RC or LC. From this direction into the inductance cell. When the capacitor starts discharging, then electrostatic charges will be converted into electromagnetic charges. Electrostatic field will be converted into the electromagnetic field. And as the current flows through the inductance cell, magnetic field will be starts developing across the inductance L in the direction which is represented in this figure. That is figure 2. Direction of current decides the direction of the magnetic field which is developed across the inductance cell. The process of developing the magnetic field across the inductance cell continues till the steady state of magnetization is reached across the inductance cell. How one can recognize the steady state of magnetization is reached? When the rate of change of current flowing through the inductance cell, that is a di by dt, becomes equal to 0, then we can say the steady state of magnetization is reached. When the steady state of magnetization is reached, the capacitor is completely discharged, whereas magnetic field is fully developed across the inductance L as it is represented in this particular figure. So this is the magnetic field which is developed, and this is done by converting these electrostatic charges into its corresponding magnetic flux or magnetic field. After steady state has been reached, and as the being capacitor is completely discharged, and as the being till it is connected with the parallel to the inductance cell, the magnetic flux across inductance cell will starts collapsing. And as magnetic field starts collapsing, current will start flowing through the capacitor C in opposite direction. And again capacitor C will start charging with the polarity opposite to that of in figure 1. That is, electromagnetic force will be converted into electrostatic force. The process of collapsing the magnetic field will continue till the capacitor will fully charged with the polarity which are represented in this particular figure 3. And finally, capacitor is fully charged. By the way, magnetic flux across the inductance cell totally collapsed and it becomes 0. When magnetic field becomes equal to 0, capacitor C is fully charged and magnetic flux will be converted again into the electrostatic force by charging the capacitor with the polarity in the opposite direction. But friends, still the capacitor is get connected in parallel with the inductance cell. switch is still closed. Now what happens is, assuming charged capacitor, this condition is same as that of figure 1. That is, charged capacitor is connected in parallel with the inductance cell, only with the difference that the charges which are stored are in opposite polarity. That is, here upper plate is negatively charged, whereas lower plate is positively charged. Now at the cost of this, the capacitor will again start discharging through inductance cell, but only with the difference that the discharging current will flow in opposite direction to that of in this particular case. That means the discharging current will flow in this particular in opposite direction through the inductance cell. Again, the electrostatic charges will be starts converting into electromagnetic field. By converting electrostatic current into electromagnetic current, again magnetic flux will be starts building across the inductance cell, but the direction of building of the magnetic field will be in opposite direction than that of in this particular case. This process will continue till steady state of magnetization is reached across the inductance cell. That means di by dt becomes equal to 0. By the way, capacitor C will completely discharges through the inductance cell. Charges across capacitor becomes equal to totally 0. No charges will be stored in it. No electrostatic charges are present. All entire electrostatic charges are converted into the electromagnetic field with the direction opposite to that of previous one. By the way, when capacitor is fully discharged, again after reaching the steady state, magnetic field across the inductance cell will again starts collapsing. When magnetic field will starts again collapsing, capacitor will start charging with the polarity as it is represented in the figure 1. That is opposite to that of this one. Means lower terminal negative and upper terminal positive because of reverse direction collapsing of the magnetic field. This will continue till again capacitor fully charges and we will get the beginning condition. That is, upper terminal of capacitor is positively charged, lower terminal of capacitor is negatively charged. By the way, when capacitor fully charges, inductance will be totally, magnetic field across the inductance will be totally collapsed. And this process will repeat continuously one after the another. In all these 4 cases, we can say always magnetic field will be converted into the electric field and electric field will be converted into the magnetic field. Conversely, we can say electric charges will be converted into magnetic field will be converted into electric field. Thus, but again with the fact that the polarity of the magnetic field as well as electric field will always in opposite direction. Thus, the charging and discharging action of capacitor and collapsing and building up the magnetic field will generate an electrical oscillations into the tank circuit. When these oscillations are given as a input to the amplifier, these are amplified by an amplifier and produces oscillations at the output, provided the phase shift between output signal generated and that of the input signal is 0 degree or 360 degree, that is positive phase has been provided and KAV should be greater than or equal to 1. Naturally, the electronic circuit designed will start to generate an oscillations. Then that circuit we can call it as it is an oscillator. Thus, by connecting either combination of R and C in parallel or L and C in parallel in the amplifier circuitry in a proper place so that it will generate the necessary phase shift and satisfy the condition that KAB should be greater than or equal to 1, then naturally it will acquire the positive feedback and start producing the oscillations, and thus we can say it produces the output without any input, or it converts DC into AC. So that's what how oscillations are going to be generated either in the LC tank circuit or in the RC tank circuit. Friends, that's all about generation of oscillations in the tank circuit. Next time, simply we are going to couple this tank circuit with the amplifier circuitry. Coupling them, this circuitry with the amplifier circuitry, we are going to study 4 oscillators, 4 or 5 oscillators consequently. One is Hartley oscillator, second one is Colbert oscillator, third one